Hello everybody, in this lecture we will be solving 2014 IMO problem number 4. Here is a view of this problem. We are given 2 points P and Q on side BC of an acute triangle ABC which satisfy this and this degree conditions. Let's go ahead and draw this picture, I would guess. So we have our triangle ABC like this, A, B, C. I should pick P on BC such that PAB, this angle is equal to BCA. BCA is the angle here. This is angle C. So it is probably like that. Yeah, why not? So that's the point P. And so therefore this angle here is C. And we are also told that, let me use a different color, CAQ is equal to ABC. ABC is this angle here, angle B. CAQ, okay, so this angle is a bit bigger, so it's probably something like that. Yeah, why not? So that's the point Q, and that whole angle here is B. And finally, we are told that we would like to pick points M and N on the sides AP and AQ respectively, such that P is the midpoint of AM and Q is the midpoint of AN. So I will go ahead and extend these lines. AP extended. That doesn't look right. Like this, I guess. So that length here. So that's the point M. And also, if we extend AQ, let's keep the same color. That's the point N. Finally, we are to show that BM and CN intersect on the circumcircle of triangle ABC. So we are to show that this intersection point here, X, is on the circumcircle, which, I would say let's chase some angles here. Obviously, observe that on triangle AQC, the external angle here is equal to B plus C. And in a similar way, the external angle here, if you focus on triangle ABP, is also B plus C, suggesting that we have, so both of these angles are A here. So therefore, we have an isosceles triangle here. So these two sides are equivalent, and we know that AP is equal to PM suggests that this one is also the same, so I can use the same decorations as well. Next, I would like to observe that, hey, for instance, if you focus on triangle, say, ABP, you would realize that the angles are C here, B here, and A here. So this triangle is I should probably say let's actually keep the order. Let's say triangle ABC is similar to triangle PBA, and also if you focus carefully, the same thing here, QAC as well, triangle QAC as well. Now I can actually make use of these two here. For instance, if I say BP to PA, yeah, so let's do it. So we have BP to PA is equal to AQ to QC, AQ to QC, but we can simply replace PA with simply PM here, so that would give us BP to PM is equal to and similarly AQ can be replaced with QN here, QC. So we have gotten a relationship between BP this side and PM this side of triangle BPM, and also between the sides QN and QC, QN this side and QC this side of triangle NQC. So all that remains is to also observe that these two angles are both equal to bivertical angles, B plus C, both of them, as a result, these two triangles also, we know that angle BPM is equal to angle NQC, and they are both equal to angle B plus C. So therefore, this would imply that a triangle, let's say BPM is similar to triangle NQC, right? Triangle NQC. Yeah, right. So, but then this implies that these two angles are equivalent, right? Angle PBM, angle PBM is equal to QNC, this angle over here. But if these two angles are equivalent, it would imply, so let's write that down. So this implies that angle QBX is equal to angle QNX, but that suggests that quadrilateral BQXN is cyclic. So we can further say that this angle over here, which is angle A here, would have to be equal to this angle over here. So that implies that angle BQN, which is equal to angle BXN is equal to, BQN is simply angle A by vertical angles, right? So we got here an angle A, but then it means that the supplementary angle here is 180 minus angle A, and we are done, because we have just shown that two opposite angles here, angle A, vertex A, and vertex X, has two angles that are supplementary. As a result, quadrilateral ABXC is cyclic, right? So that solves the problem. I would like to also provide an alternative proof to that same problem. So let me go ahead and draw the picture one more time. This one will be a projective proof. So we have again our triangle ABC. Let me actually do it like this. ABC. And as usual, we draw our points P and Q, and then we extend them, right? So this one I believe is called as N, and this one is M. And next is I will reflect, and obviously we know some angles that are equal, obviously, and B and C. So this guy here is B. This guy here is equal to angle B, and this whole, not the whole thing, just this much, is equal to angle C. Now, and obviously we established earlier that these two are equal, so, and these two are also equal. So what I have in mind, so as a result, NM, the line NM, is parallel to BC because BC contains PQ, and PQ is the midline of triangle ANM. So therefore this line is parallel to this line. It's no surprise that if I reflect point A across BC, it will fall on that line. So A prime, let me call it, and these angles are preserved. So this is angle B, this is angle B. I just reflected BA to BA prime, and CA is reflected into CA prime. So this is angle C, this one is also angle C. But I hope it's clear that point A prime, which is a reflection of point A across the side BC of our triangle ABC, is on the line NM. Now I would like to consider the points, the point X, obviously. So we would like to confirm whether this point X, which is at the intersection of the lines BM and NC, is on the circumcircle of triangle ABC. In fact, I would like to take the time to draw that circumcircle. Oops. And obviously I don't know if it will go through X. And then let me do it like this actually. That's a pretty bad sketch actually. So let me just revise it just a little bit. Yeah. Yeah, for now I don't know what's going on around here. So let me just draw it like this. It definitely goes through the point B. So I'm drawing the circumcircle. I claim that these 2 points also are on that circle. Just call this point as L and this point here as K. Focus on the angle LBC. Obviously angle LBC, which has degree B here, because recall that BA prime was just a reflection of AB, right? So, or BA, I should say. So because we got the point A prime by simply reflecting A across BC, so this is angle, so let me write that down. So angle LBC is equal to angle CBA, CBA. But notice that angle CBA is the same thing as angle QAC. It's given in the problem, QAC, but QAC is the same thing as LAC, angle LAC. But notice that angle LBC and LAC, both being on the circle, they subtend the same arc LC. As a result, L must be on that circle. L is on the circumcircle here. So I hope that's clear. And we can use a similar trick to observe that K is also on that circle, right? K is the intersection of PM and CA prime. So obviously if you keep track of this angle here, which is C, it measures C as we did earlier, but this is also equal to this angle, and notice that that's equal to this angle C as well. But KCB and KAB, they both subtend arc BK. As such, K is on the circumcircle as well. So all that remains is to show that X is also on that circle. But now I can easily apply Pascal Theorem. Recall that Pascal Theorem, basically just a simple reminder, if you have 6 points on a circle, let's name them as A prime, B prime, C prime, and ABC. And then if you connect those points in pairs like this, A and B's, A's and C's, and then finally B's and C's, we will get the following points. A's and C's and B's and C's will give me these points. So the claim is that these 3 points are collinear. Okay, obviously here these 3 points, if you call U, V, W, so U is simply equal to A and B prime intersection A prime B. V is equal to A C prime intersection A prime C, and W is simply equal to B C prime intersection B prime C. So that's Pascal theorem basically tells us that U, V, and W are collinear. If these 6 points on the circle such that their intersection are labeled as U, V, W, U, V, and W are collinear. But this is an if and only if statement, by the way. Now, if you look at our circle here, we have already 5 points. 1, 2, 3, 4, 5. And if you extend those lines, these 5 points, and consider this candidate X. Notice that their extensions, for instance, AL and CX, they meet at N. BL and CK meet at A prime. And finally, BX and AK meet at M. As such, we clearly see they are collinear. We claimed earlier that A prime is on the line NM because it's simply a reflection of the point A across BC, and QP being the midline, so this clearly shows that A prime is on that line. Because N, A prime, and M are collinear, this forces point X, by the converse of Pascal theorem, to lay on the circle as the 6th point of that of the Pascal theorem, and that proves the problem again. Hope you enjoyed the video. I'm looking forward to see you guys in our next lecture.